damp oscillation. We know that, student, damp oscillation is nothing but what? Whose amplitude is decreasing with respect to time. That is nothing but your damp oscillation. Or one more thing also which we can say, its amplitude are decreasing just because of its air resistance. So here we have to see about its diagrammatic explanation. So this is rigid support, spring, block and vane. That is damp oscillator. Now if the amplitude of oscillation of an oscillator is reduced by the application of external force, the oscillator and its motion are said to be damp oscillation. This is nothing but your damp oscillation. So period of oscillation gradually decreasing amplitude are called damp harmonic oscillator, and oscillator is called damp harmonic oscillator. For example, motion of simple pendulum dies eventually as air exerts viscous force on pendulum and there may be a fraction. Okay, so there may be some friction at the support. So from this figure, okay, which we can say that block of mass m that can oscillate vertically on a spring. So from the block, a rod extends to a vane that is submerged on a liquid. So this vane is inside a liquid. When moves up and down, the liquid exerts a drag force on it. So its opposite sides, liquid exert a opposite force act on it. So mechanical energy of the block spring system decreases with time as energy is transferred to the thermal energy of liquid and vane. So this force will be damp force. So this force we have to consider this as a damp force. Look at here. Damping force depends upon the nature of surrounding medium and is directly proportional to the speed v, vane, and the block. So Fd is equal to minus B into V, where B is damping constant and negative sign indicates Fd are opposite to the velocity. So damping force and velocity are in opposite direction. So for spring K, spring constant K, the force on block from the spring Fs is equal to minus Kx. Assuming that gravitational force on the block is negligible as compared to Fd and Fa, so total force acting on the mass at any time is equal to what? F equal to Fd plus Fs. So we know that F equal to Ma, that is Newton's second law. So Ma is equal to minus Bv minus Kx. So take both the minus sign on left hand side, it will be Ma plus M plus Bv plus Kx is equal to 0. We know that A is acceleration, which is d2x upon dt square, V is dx upon dt plus Kx is equal to 0. So which is your required equation, and solution of this equation 5.35 describes the motion of block under the influence of damping force which is proportional to the speed. So you can see this equation. Solution is found to be in the form of x is equal to a e to the power minus bt upon 2m into cos of omega dash t plus phi, where this a e to the power minus bt upon 2m is the amplitude of damp harmonic oscillator, which is amplitude, and this wave will be what? Cosine wave, which always starts from extreme position. So from this figure, which we can say that displacement against time graph. So see this figure, this amplitude is decreasing as time increases. So as shown in the displacement against time, amplitude decreases with time exponentially. So this is also called exponential decay. Okay, so term cos omega dash t plus pi shows the motion is still in SHM. So this cosine wave indicates this wave always in SHM. So the angular frequency omega dash is equal to what? Under root k upon a minus b upon 2m bracket square. Okay, b upon 2 twice m bracket square, that is your angular frequency, and period of oscillation t is equal to 2 pi upon omega, where omega is equal to same term, that is we have seen angular frequency, which is equal to under root k upon a minus bracket B upon twice M bracket square. So damping decreases with increasing the period, which slows down the motion and decreases the amplitude. So as time increases, okay, its amplitude will be decreases. Fine. Okay. Thank you, student. Is free oscillation, force oscillation, and resonance. So free oscillation is nothing but what? Oscillations which are free. So body which can move freely to and fro motion, that is also we have seen. That is the starting part of this chapter. So free oscillation is nothing but if an object is allowed to oscillate or vibrate on its own, it does not so with its natural frequency. So that is nothing but your oscillation. For example, if the bob of simple pendulum length L is displaced and released, it will oscillate only with the frequency n is equal to 1 upon 2 pi under root g upon L, which is derived equation in last lecture. So that is natural frequency, and oscillations are free oscillation. So by applying a periodic force, the same pendulum can be made to oscillate with different frequency. So the oscillations then will be force oscillation, and frequency is the driver frequency or a force frequency. Now we have to consider arrangement which shown in the figure, that is in figure 5.15. There are 4 pendula tied to a string. See these 4 pendula A, B, C and D. Okay. Now A and C are same length, B is shorter and D is longer. But pendulum A is a solid rubber as its bob and will act as the driver pendulum or source pendulum. Means what? Okay, we are going to start oscillation with this pendulum, so that we call it as a driver pendulum or source pendulum. Okay, then another 3 pendulums. Okay, these are a different pendulum. So we call it as a hollow rubber balls as their bobs and will act as a driver pendulum. So A and C are same length, their natural frequencies are same. Pendulum B has higher natural frequency and it is shorter, and pendulum D is natural lower frequency than that of A and C. Okay, so because B whose length is a very low as compared to A and C, and pendulum D whose length is high, so that frequency of B is higher as compared to D. Now if pendula A is now set into oscillations in a plane perpendicular to the string, in the course of time it will observe that the other 3 pendulum also start oscillating in parallel planes. This happens due to transfer of vibrational energy through the string. So oscillation A, free oscillation, those of B, C and D are force and same frequency as that of A. So the natural frequency of pendulum C is same as that of A. Why? Because A and C both are at same length, as it is of same length of A. Now we can see that among the pendulum B, C and D, pendulum C oscillate with maximum amplitude, other 2 with smaller amplitude. So energy depends upon its amplitude. It is clear that pendulum C has absorbed maximum energy from the source pendulum A, while that of other 2 absorb less. So it shows that object C having the same natural frequency as that of the source, so it will absorb maximum energy from the source. So in such a case, it is said to be in resonance with the source, that is pendulum A. For unequal natural frequencies on the either side, that is higher or lower, the energy absorbed is less. So if the activity is repeated, a set of pendula of different length and square of their amplitudes are plotted against their natural frequency, the plot will be similar to that of in figure 5 and 16. So peak occurs when force frequency matches the natural frequency. Okay, force frequency, that is nothing but what? Applied frequency. Okay, which is applied to natural frequency, then we call it as a resonant frequency. So see this graph. Okay, amplitude A square versus frequency. Okay, so this dotted line indicates at its top which is resonant frequency. So in chapter, okay, superposition of waves, okay, all we are going to see the most traditional musical instruments use the principle of resonance in the topics AC circuits. So the resonance in the AC circuits is also discussed. But remember, this FR is nothing but your resonance frequency.